If I don't want to solve them in detail, why should I derive these 4 rate equations? Okay? Because I want to show you the steady-state solutions. Complete solutions means you can not only know steady-state behavior, but also dynamics. But it's too complicated. Here, I just want to focus on steady-state behaviors. Then, the 5 rate equations can be simplified. That analytic solutions are possible. If you stay with the original 5 dynamic equations, no analytic solution. You need to rely on numerical solutions. Okay, but it's very difficult to see the general behaviors by numerical solutions. I prefer analytic solutions. Okay. So what happens in steady state? First, number density has a time derivative of number density. Each number density has to be 0. So I can quickly drop these 4 terms to 0, which greatly simplifies the equations. But why is this true? Is it okay for you? Because in steady state, what is steady state? Dynamic balance. Okay? So although number densities could be non-zero, but no change with time anymore. That is steady state. Okay. So I can quickly drop them to zeros. Secondly, I know N1 must be much larger than N2. N3 must be much larger than N4. Why is that? Let's take a look at the view graph. Because of 2 quick relaxation processes. Compare with N1, N2 is very small. Because whenever electrons are here, they cannot stay there. Quickly dump to level 3. So if you observe, if you monitor the electrons on level 2, almost nothing. And similarly, quick relaxations between levels 4 and 1 means almost no electrons here. So N2 and N4 must be much smaller than N1 and N3. Okay. In that case, we can further simplify the equation. Okay. Say this term can be dropped because compared with N3, this is very small. So the difference is very close to N3 itself. For the same reason, this term can be dropped to 0 by approximation. Okay? Then we start with equation 2 prime here. In equation 2 prime, if this is 0, you can represent N1 in terms of N2, right? You got this equation. And by equation 3 prime here, because these 2 terms are already 0, so you can represent N2 by N3. Okay? In equation 3 prime, there are only 2 unknown number densities, N2 and N3. So you can represent N2 in terms N3. Then, by equations 2 prime, 3 prime, and 5 prime, you can represent N3. You can solve N3. Okay? If you check equation 5 prime, you know N1 plus N3 equals some given constant Ng. But according to here, N1 is represented by N2. N2 is further represented by N3. In other words, N1 is already represented by N3. So you have something about N3 plus N3 equals a given constant. That's why you can solve N3 analytically. Okay? So this is nothing special. This is the common technique that is used in solved system of algebraic equations in the middle schools. Right? 你不是在学那个联立方程组，你不是会用代入消去法。This is the same. So you got solution about N3. But why N3 is very important? Actually, it's N3 minus N4 important. So let's try to solve N4 using equation 4 prime by the same strategy. And under this condition, which is usually true, N4 can be represented by N3 as well. Then, combining the last two results, you can write down N3 minus N4 as this formula. Basically, you solve the difference between these two number densities already. You have analytic solution. But why are we interested in N3 minus N4? Why? Why don't I pay attention to N1 or N2, but N3 minus N4? Do you know that? Because we are talking about lasers, and the central transition of our interest is the laser transition, which is transition from level 3 to level 4, right? So this is the so-called population inversion, right? If you have a positive number here, you got population inversion. And the least quantity must be related to the optical gain you can have. The larger the population inversion, the larger the optical gain you can have. So we are interested in this quantity because we are interested in solving the laser gain analytically. Okay, so this is a physical quantity of our interest. Okay, now I want to show you the formulas about saturated gain. The saturated field gain, which is defined here. If you feel it's very strange, just using another way, the ratio between output electric field to the input electric field is equal to exponential to the g. Okay? Because it's a ratio between fields, so it's field gain. It's not power gain. Okay? If it's about the ratio between powers, you are talking about power gain. But here, we are talking about field gain, the ratio between output and input electric fields. Okay? And small g is the field gain coefficient, as I mentioned before. And this quantity g is proportional to the product of population inversion and effective volume, Vg, which is shown here. Population inversion times effective volume over constant 2 is defined as the gain coefficient, small g. And the Vg is defined here. Cross-sectional area, as we just introduced earlier, working distance, Lg. Okay? Although the physical units is correct. This is area, this is distance, so the product is volume. But you must be curious about why this formula is reasonable, right? Again, I show you one supplementary slide. 我用了4步告诉你为什么这件事是对的。Consider a light beam of intensity I, but this is not a constant. It's a function of position. It can be X or Z. For the time being, maybe I use a symbol X. Okay? At the position X, the light intensity is I. If there is amplification, you can imagine this is not a constant but an increasing function of X. The light intensity will be stronger and stronger. Okay? And the beam cross-sectional area is a constant A. And we consider propagation over a very short distance, delta x. Then, what is the meaning of the product I times sigma g? We have seen this before. This is the stimulated emission power contributed by a single ion around position x. We have seen this, right? Then, a new physical quantity, say Q, is population inversion times the stimulated emission power due to single ion. And what is the meaning? 只有这个叫做一颗离子贡献的 stimulated emission power， 你再乘上这个叫做 number density， right？ Number density 意思是单位体积有多少颗 ion。一颗 ion 的贡献再乘上单位体积的 ion 叫做什么？单位体积的 power， right? So the power emitted per unit volume is Q. Okay? Then the power will increase by this amount. Okay? Power due to power emitted per unit volume times the effective volume means the emitted power. Okay? And the effective volume is the beam cross-sectional area, big A, times the propagation distance, delta x. So this is a volume. And this is power per unit volume. So the product is the power generated within a short distance, delta x. That's why the new power minus the old power should be the power difference. Okay? What's next? Spatial derivative. P prime of x is the power difference divided by the propagation distance. And if delta x is very small, this is derivative about variable x, right? And delta p is this one over delta x here. So the right-hand side, you simply got q times a. But q is already here. You write down q, regroup them. You got this one. And I times a. I is the power per unit area times the beam cross-sectional area. So this is the product I times A is power itself. So actually you got a differential equation, right? P prime of x equals a constant n3 minus n4 times sigma g times the unknown function p of x itself. This is a first order ordinary differential equation, which can be easily solved. We know the solution is an exponential function, right? So when the propagation distance is Lg, the working distance, you got this result. Output power equals input power times an exponential function. And the propagation distance is a constant, Lg. Okay? And the sigma g times Lg is already the effective volume as we defined before. And the power is related to the square of the electric field. Okay? So that's why you have a constant 1 over 2 here. Okay? There is no 1 over 2 in the power gain, but there is 1 over 2 in the field gain because of this relation. Okay? Then you got the answer. gain coefficient G is equal to this one is fully justified in this slide. Okay. So now, this formula is no longer a mystery, but fully justified formula. You just borrow the formula in the previous slide. We have solved this one, right? N3 minus N4. Just copy it here. Then you got this result. The gain coefficient G, remember this is the field gain coefficient formula. It's governed by this one. And you can see the gain is a function of W and S. W is pump rate. S is the stimulated emission rate. And the stimulated emission rate is certainly related to light intensity, according to the definition. So your saturated gain is dependent on two things. One is how strong the pump is. Of course, the stronger the pump, the larger the gain, intuitively. Also depends on the emitted light intensity. In principle, the brighter your light intensity, S is larger, you will have a smaller gain coefficient due to gain saturation, as I mentioned. Why you have extra photons? You pay the price. The price is the reduced gain. So if S is larger, actually you will have a smaller gain coefficient. Okay. And there is a new quantity G max here, which is equal to total number density of the material, effective volume over constant 2, and its upper bound of the gain coefficient. The reason is this number is always smaller than 1, so your gain is always less than the upper bound, G max. Okay? So it's upper bound. All you have to do is substitute the formula of N3 minus N4 derived in the previous page into here. You can get them. It's very straightforward. Okay. But let's talk about the gain formulas step by step, starting with small signal gain. Okay. When the pump is too weak, your gain is smaller than the cavity loss. In this case, coherent light cannot build up. That means gain is too weak. So maybe you got some amplification, but it's insufficient to compensate for the loss of photons. So you cannot build up the coherent light. There is no lasing. In that case, lasing light intensity I is 0. As a result, stimulate emission rate S is also 0. In this spatial case, the corresponding gain G when light intensity is dark is coined as small signal gain with a spatial symbol G sub 0. Okay? And if you borrow the formula in the previous slide, this is the original formula. When S is 0, what happens? You can cancel these two terms, right? Then you got a simplified formula like this: W over tau G inverse plus W times upper bound gain, G max. And so the small signal gain formula is the upper bound over 1 plus a positive number, W times tau G parenthesis inverse. Okay, this is the small signal gain formula. And as I mentioned at the beginning of this semester, I prefer not to remember this formula, but use some curve to impress. Okay, this curve is plot is plotted against the normalized pump. That means to the right-hand side, you got stronger and stronger pump. And your vertical axis is the normalized gain. To the upper side, you got larger and larger gain. And the curve is like the blue curve. Simply speaking, when your pump is 0, you have no gain. When your pump is increased to 1 unit, which means pump rate times tau g constant equals 1, or pump rate W equals 1 over tau g, the same thing, your gain is 50% of the maximal gain. But if you keep on increasing your pump, although your gain can be larger and larger, but no matter how hard you pump the gain medium, your gain can never be larger than the upper bound, Gmax. So this is a curve that never crossing the ceiling. And it's totally according to the formula we just derived. Now, one bonus question. What is the physical meaning of the upper bound? Why there is an upper bound? Yes? Perfect. Okay. The limit comes from the total number density. It's a fixed constant. No matter how hard you pump your gain medium, the best you can reach is all the electrons already distributed on level 3. That's it. Even you pump it even harder, you cannot get an even larger gain. That's the physical limit. Okay. 所以不要死记这个 formula。你看这个 curve 的长相，然后了解它的物理意义。为什么有一个上限？电子数是固定的，无论你 pump 的多厉害，最多就是全部送上 upper state， 再也没有额外的 gain 可以得到了。That's why this curve is always below the Gmax. Okay, the small signal gain formula here implies some things. First, the small signal gain depends on the pump W here, but not on the light intensity I, because there is no I in the formula. It's reasonable because small signal gain means the gain when there is no coherent light intensity. Okay? Secondly, gain arises whenever there is some pump. According to this formula, as long as W is a non-zero constant, some positive number, G0 is already positive. That means you can immediately have gain when there is any pump, no matter how small is it. Okay? But remember, this is a proprietary merit of four-level systems. This formula comes from four-level system model, right? If you are interested, you can analyze the corresponding formula for three-level system. You will get a very different story, because in that case, pump has a threshold. Your pump has to be larger than some minimum number, then you will have non-zero gain. Before that, you will have negative gain. It's still loss. Okay? Here, I just skip the analysis about three-level system. I just want to remind you, this is not always true. It only applies to four-level systems. Okay. A gain medium of longer lifetime, tau g, can have a larger small signal gain at the same pump rate. Just look at the formula. If tau g is larger, for the same pump rate W, the product is larger and the inverse is smaller. And a smaller number in the denominator gives you a larger small signal gain, right? This is advantageous to get lasing because you need certain small signal gain which is larger than the cavity loss to get lasing. And a gain medium with long lifetime means with the same pump rate, you can get larger gain and easier to get lasing. Okay, so when you try to find some suitable gain medium, it's a guideline. Longer lifetime constant is advantageous in gain lasing. But in other aspects, it could be disadvantageous. Okay, I only mentioned that it's easier to get lasing, but I do not guarantee it's always better to have a longer lifetime constant. Okay. Saturated gain. When the pump is above the threshold, we have lasing. So stimulated emission rate is positive, but we also assume the pump is not too strong, so stimulated emission rate has to be much less than 1 over tau for 1. This is an extra condition we have to meet. Then the saturated gain coefficient formula can be simplified to this one. Okay. Without this condition, the formula is even more complicated. So we restrict ourselves to this case. We got an easier formula. Then you can substitute Gmax by this one, S by the definition which we have introduced already. Okay? Then you got a very easy formula. Saturated gain is approximately equal to the small signal gain G0 over 1 plus a ratio. I is the light intensity in the cavity. I set is defined here. The meaning of I set will be clear later. But you can see, according to this formula, the denominator is always larger than 1. That means G is always less than G0, right? Whenever you have light, coherent light, you will have a smaller gain, smaller than the small signal gain. Okay? And the meaning of saturation intensity is when you're intracavity means inside the cavity. The light intensity inside the cavity equals to saturation intensity. You got 1 plus 1 in the denominator, right? In that case, your saturated gain is 50% of your small signal gain. Okay, so the physical meaning of saturation intensity is when the light inside the cavity equals to this number, your gain is reduced by 50%. Or gain saturation is evident when light intensity equals to saturation intensity. Finally, since in steady state, this condition is always true. Okay? So you can, using this formula, to write down the steady state intracavity light intensity governed by this formula. So a bigger saturation intensity tends to give a stronger steady state light intensity because it's proportional. 一个比较大的饱和光强度，通常也就代表你最后出来的光会比较亮。Okay, so when you choose gain medium, it's another guideline. If you want to build a very intense laser, maybe you need to find some gain medium with large saturation intensity. But if you want to design a laser that can be easily get lasing, you need to find some gain median with long relaxation time, tau g. So it's different. Okay. Okay, let's stop here.